Thank you all for coming. This is a webinar on easy simulation tools built within SOLIDWORKS for instructors. I'll be your presenter today. My name is Shaun Bentley. I've been using SOLIDWORKS and simulation since around 2006, so about 14 years now in this role. Primarily my roles have been to do technical support, training, and a variety of other miscellaneous activities. But pretty much my area of interest, my area of expertise is on the simulation side. That's where I've spent a great bulk of my time. I'm a mechanical engineer by trade, and since I graduated, I've been moving into the simulation realm. So to get into our actual content, what I plan on covering with you is the different tools that are available with SOLIDWORKS EDU and with student licenses. And with those licenses you get quite a bit. You get pretty much every single simulation tool that we offer to SOLIDWORKS premium commercial level licenses. So these are really high-end tools that are available right within your SOLIDWORKS EDU and SOLIDWORKS Student Edition environments. So those tools range from running probably the most popular, the linear static analysis for assemblies and for basic parts. But also goes all the way up to being able to run full-blown nonlinear and dynamic structural analysis, and a lot of things in between. A pretty big list of different tools. Now, I'm not going to have time to cover all of these today. We're going to pick a subset of these tools, and I'll kind of show you give you a little bit of taste of how easy it is to set up a simulation using some of these tools, so that you and your students can start to incorporate it in some of the learning curriculum. Now, a few of the other tools that are included with your SOLIDWORKS EDU and SOLIDWORKS student editions. You also get access to a fluid dynamics tool, flow simulation, and also plastic injection molding tools. So this flow simulation tool is also very popular with students, being able to simulate airflow, heat flow, and that's another one that we'll go over. So my agenda for today is going to talk about this little subset here of the tools I just showed you on those previous slides. I'll show you with an example of running static structural analysis to figure out stresses, calculate stresses, and also deformations. Run a time-based motion analysis to see assembly motion, calculate things like motor torque. We'll run a vibration study using our frequency analysis tool, and finally we'll take a look at running a flow simulation study to calculate drag and maybe also some heat transfer, time pending. So got quite a bit to cover, so let's jump right in. So the first tool I'd like to cover with everybody is this linear static analysis for assemblies. Okay, being able to run structural analysis. So what I'll show in the coming demonstrations is how do I set up a simple analysis on just a block with a hole in it and calculate a stress concentration. So this might be a good thing for some of your classes on structural mechanics when you're talking about stress concentration factors. Or even we can do cantilever beams, do a test on a cantilever beam, look at beam stresses, and or trusses. You can build trusses in SOLIDWORKS and look at those. So that way I'll look at a beam element example as well, this Formula SAE frame. Okay, so that's one popular senior design project that many students get involved with. So I'll talk a little about some of the content that's available to those students and how we might set something like that up as well. So to start with, so what I'd like to show you first is setting up a simple analysis. Now I'm going to assume a little bit of at least a basic level of familiarity with the SOLIDWORKS CAD environment. I won't draw too many blocks. I'm going to have pre-constructed geometry. What I have here is a simple block with a hole in it where I'm going to put a tension load on it. My plan is to fix one side, put a tension load on the other side, and just show you how easy it is for you to set up these studies on yourself. So in order to set up structural studies, your SOLIDWORKS environment has this SOLIDWORKS add-ins tab usually right across the top, where you can go to get access to a lot of the tools that I'll be using in this presentation. The one I'll use for a lot of our structural analysis studies is this guy here, SOLIDWORKS Simulation. So if I click on that button, it'll activate that piece of software. It has to boot that up, and you'll see a couple of interface items will get added to my SOLIDWORKS CAD seat. First of all, a simulation tab gets added onto my command manager, but also a simulation drop down gets added up in the top here. Okay. So once that's all booted up, now I'm ready to set up and run my structural analysis study. So similar to how if you want to create a new file in SOLIDWORKS, you'll go to File, New to create a new file. Well, in Simulation, if you want to create a new study, you'll go to Simulation and create a study. And then here you see the list of all those, basically all those different study types I showed you on that earlier slide. Static, frequency for vibration. These are probably the two most popular structural analysis studies. That's why we put them in the top. So I'm going to start off with just a static analysis. And as soon as I do that, now you see the SOLIDWORKS tree. Let me kind of expand this down. You can see the SOLIDWORKS tree up here, and then the simulation tree here. It breaks my tree up into two subtrees. So that way, if you ever want to make change to your geometry, you can come right up to your SOLIDWORKS tree, make a quick tweak to a dimension, and then come back down here and rerun your study. I'll show how easy that is in a moment. So what I'll do though is I'm going to work with this simulation tree here, basically from top to bottom to set up the study. And if I just go through each of these menus, we'll be able to set up the study pretty quickly. So starting with the top item here, where it says rectangular hollow plate, it shows a body. This is where I go to assign material to this body. Now if this was an assembly, you'd see multiple bodies listed here. But since it's just a single body part, I just need to apply material to just that one body. So I'll go ahead and put make this thing out of steel, ASI 304. Apply that and close my material dialog. Okay, so now I've got my steel applied to that. By the way, the yield strength of this material that I'm going to be watching out for when I run this study, it has a yield strength of about 207 megapascals. Now I'm going to go ahead and put a fixture on one side of this model. I'm going to restrain it on the left, so I'll move down to my fixtures folder and add fixed geometry to this side. So that'll hold it down there, and then I want to put tension on the other side. So I'm going to add a external load, a force. So again, you can really, my main point here is see how easy and intuitive that a lot of these steps might be. I'll kind of backtrack over some of this in a moment just so you can see what I'm talking about there. But I'm going to do 25,000 pounds in tension, and I'll click OK to that. So basically, you just follow the steps if you want to set up your own study. You start at the top. Apply your material, apply your fixture, apply your load. Okay, and for a simple part like this, of course, it's almost trivial. If I go up here and hit run, okay, it'll go ahead and mesh the model and run the study, and here it gives me 3 result plots: stresses, displacements, strains. All these it just outputs automatically based on whatever my simulation template is set up for. So what I like to do though is I can customize my template a little bit. You can see these units over here, a lot of scientific notation. So if I just go over here and I double click on the chart, that allows me to edit a lot of those chart details, tweak things such as like exactly how the colors are displayed. If I want them to be more optimized for color blindness, it breaks the scale up a bit better. If I don't like to read scientific notation, we can change it to floating with a couple of decimals. And if I want to make the units more readable, instead of using these tiny units, we can use megapascals. So a lot of that stuff can be customized right on the fly just by double clicking on this feature over here. I get access to being able to change all those chart options. And then here I can now see pretty clearly how is this block doing. We have a maximum stress of 420 megapascals. I can turn on a little annotation just by clicking on this number up here. I can turn on this little annotation that points to where that's at. 420 megapascals, and my yield strength is around 207. So it looks to me like we've got a problem with this part. And what I'd like to do here is maybe change this peak number to 207. So that way we can see exactly how bad this thing is. And really it looks like we're going to have a yield region right here, if not a little bigger than that. It's going to be yielding locally. But it doesn't look like it yields all the way through the thickness. So it looks like it's going to be able to hold that 25,000 pounds, but we're going to have some permanent deformation. So these are the type of topics that you may be able to incorporate into some of your classes, being able to run a quick study like this. You can kind of see the process here, just setting up your fixture, load. You can imagine doing this on a cantilever beam, run a quick study, show your students a comparison to a book result, and then also show them next level. Here we can add more parts to this and see, does it make a difference, and something that you wouldn't be able to feasibly do a hand calculation on, we can very quickly set up that in simulation as well. So that one was pretty straightforward. Let's move on to another example which uses more than one single body. Let's try out this frame here, and you'll see basically very similar steps to what I showed you a moment ago. This model was pulled directly from our design library SOLIDWORKS content here. With the SOLIDWORKS student editions and with the EDU editions, you have this under this little stack of books. Under the SOLIDWORKS content, you have curriculum. Okay, now you don't have this with the commercial versions. Just the student and EDU versions have these extra tutorials, let's call them. And this model was pulled right from the curriculum. You can see if I go into like some of these folders here, I've got an SAE car project where I clicked on that to download this file, along with a training manual. It has a whole PDF included, which will walk you through step by step how to set up some of these studies that I'm showing you. To show you though, as far as setting up a structural study on a frame like this, we'll follow some of the same steps we did before, where we'll create a new study. It'll be another static analysis. And my objective in this model is to figure out torsional rigidity. Okay, it's a very common metric that when you present your Formula SAE car to the design evaluators during competition, they're going to ask you, what is the torsional rigidity of your frame? Okay, so we've got a tutorial that's built right inside that curriculum that walks you through the steps of calculating torsional rigidity right for that purpose. So in order to calculate torsional rigidity on this frame, you can see automatically SOLIDWORKS Simulation converted these bars, these weldments, into beam elements, and I can tell because of these joints, these little purple dots that popped up. Those weren't. Let me go back to my model tab for a moment, because you're not going to see them there, right? So here's my SOLIDWORKS model. As soon as I get into my simulation study, all my studies are stored down here. As soon as I get back into that, all these beam joints pop up. Okay, that tells me it's going to convert all these bodies into beam elements. Now that's really handy for me, because that way I won't have to create a really tiny mesh on every little feature and facet. It's going to really simplify the setup quite a bit, and you'll see exactly how simple it'll be. Let me go ahead and set this study up. So first thing what I'll do is these components here, these are not going to be welded to my frame necessarily. This is like my suspension. These are going to be bolted, but they'll be pinned, so they'll have some freedom to move about a little bit. Okay, but everywhere else there's going to be welds. So I want to treat these joints that we see in these corners a little different than when I want to treat all the other joints. I want to treat these like they're more like pinned joints. This guy is going to be pinned to these locations, so they'll be free to kind of pivot up and down freely. Now in order to do that, I'm going to select this beam here, and that'll highlight the beam that I want to modify in my tree. And I'll go ahead and make a change to it. If I edit its definition, I can change it to a truss. Okay, so this creates a pinned connection rather than a welded type of connection. Okay, so think if your students are designing a bridge. Okay, they're going to design their bridge maybe using the SOLIDWORKS weldments features, but then they'll want to convert a lot of the beams into truss elements if they're going to be pinned joints. Okay, so I'm going to convert that guy into a truss, and I'll just repeat the process for a lot of these other beams. Just by picking at it in the display, I'll be able to find it in my tree here and then convert it into a truss. So it is a little bit manual. If you want to convert everything into a truss, you can group select things, but it's just that the order of my tree is a little bit all over the place here based on how I drew the model. So I will have to kind of use a little bit of this approach. And you can tell which ones I've converted into trusses based on the little icon it puts in front of them. So let me go ahead and take care of the remainder here. Looks like I just got 3 more to go after this one. I think if I group select here, 69 and 40. Okay, these are 2 there and there. Those will both be trusses. Okay. And I guess I didn't grab that guy. 40 truss, and finally last one but not least, truss. All right. So with that, now everything else is going to be welded, so I don't need to convert anything else into trusses here. For my next step, I'm going to assign material to all those bodies. Everything's going to be made out of steel. Okay, not going to be welding aluminum on our frame. So we're going to use that same ASI 304 that had that yield strength of 207. Now, next, the joints. This joint group folder, it automatically recognizes where there's going to be welded connections. It's where it's saying that this guy is going to be joined to that guy. And since I'm leaving them as beams, it's going to automatically weld them there. So it's automatically recognizing all those joints. And if I wanted to edit any of the joints, that little document over here will explain a little bit of how to edit. I'm not going to get into that necessarily here. I think all the joints that it auto-recognized look pretty good. So I'm going to move right on to my fixtures. And we're going to fix the back here. Just these back, basically our differential case, okay, on the rear here. I'll blow the symbol settings up a little bit so you can see them a little more easily. So those are fixed. And then now for my force, in this case I'm going to put a force onto this beam joint here and that beam joint there. Now whenever you're dealing with beam elements, I will have to select the joint option if I want to apply the force to joints. Okay, so I'm going to go ahead and select that joint, and I'm going to have this force be pointed downward. So I'll use a reference plane, like if I use this front plane here, this front plane, that way I can point my force normal to it, normal to plane. See a little button specifically for that, and now I get a little purple arrow that pops up. Okay. So once again, I'll make that symbol a little bigger. I want it pointed down though, so I'll flip it over. And I did a hand calculation to figure out I wanted to apply 100 Newton meters of torque. It's my objective. I want to see 100. If I put 100 Newton meters of torque on this, how much rotational displacement do I get? So I can figure out torsional rigidity. It's just going to be that torque divided by the circumferential displacement, or the angular displacement, really. Okay. So here I'm going to apply as enough force such that I get 100 Newton meters. So I had to do a little hand calculation to figure out that this force needed to be 169 newtons, because that's like roughly how, depending on how far away it is from the lever arm. Okay. And then since I'm going to create another one of these forces on the other side, because I don't just want to apply a downward force, I want to put an upward force over here, I'm going to turn on this push pin, so that way when I hit OK, it wants me to create another force. It keeps this property manager pinned for me. So I use the same conditions there. I'll flip that one. That one will be up. So there we go. Now I've got my two forces on there. Just make sure that guy is right where I had it. Yep. It's up and down, so that'll twist this thing. And with that, that's pretty much it for that setup. So you see, it's pretty similar to how I set up that block with a hole in it. Put fixtures on it, put loads on it, and then we'll go ahead and run it. So if I just click run, it'll go ahead and mesh it. Breaks it up into little bits and pieces. Okay, my mesh resolution I'm just using is a default resolution, which is good enough for simple problems. When you get more complex ones, then you'll need to maybe play with the mesh a little bit, refine it to get more accuracy. But here you can kind of see that mesh, each one of these little beams here, these little circ cylinders. That's what we call a little mesh element. They're little line elements that take on the properties of whatever that weldment profile was. So if you use square tubing or circular tubing, these elements will take that into account. And then here we can see the displacement. I can see, of course, these points where I put the load, that moves the most. If I go ahead and animate it, okay, see that twisting. Now the joints, they kind of get in my way a little bit. Let me hide those joints so we can see that animation a little more clearly. Okay. Now, of course, this exaggerates the scale. You see that my deformation scale is set to about 63. So it really drastically exaggerates that scale quite a bit, just so I could see my deformations on screen. So now a lot of the reason why this one seemed really easy to run too. Now a lot of the reason why this one seemed so easy was because we let SOLIDWORKS Simulation convert everything into beam elements for us. If we had tried to do this with the same elements that I used on that block with a hole in it, this would have been a lot more labor intensive. I would have had to make sure a lot of these little corners are all cleaned up and coped, and do a nice fine mesh in a lot of these areas. But because I use the SOLIDWORKS weldments tool to make my frame, SOLIDWORKS Simulation automatically converted my frame into these beam elements, these simplified beam elements, and made the setup very easy. Okay, so if you use your SOLIDWORKS structural member tool, the weldments tools in SOLIDWORKS, it'll make running these structural analyses a lot easier for you. Now you will lose a little bit of that detail. Like if you did want to really look at stresses on a weld, then that becomes a bit more of a process. Okay, and we'll have to direct you to some tutorials on that. But at a basic level like this, real quick and easy to set up. Now this tells me my displacements, my peak displacements, resultant peak displacement. Now technically I should maybe show you one more step here of showing circumferential displacement. If I want to see displacement, let's say around an axis, I can do that as well by asking for a specific direction for displacement and selecting that axis that I want to measure my displacement around. So many of your students will want to know what is the circumferential, or what we call the tangential displacement. Okay, and that'll tell me specifically how much displacement did it go around the axis, so I can figure out how many degrees did it therefore move by based on its distance from the axis. Do a little bit of trig, and that'll be part of the hand calculation portion that your students will have to be responsible for. Do a little bit of trig to figure out, okay, based on this displacement, and the angle must be this, and therefore my torsional rigidity is, say, 1,000 Newton meters per degree. Okay, they can come up with that number. The actual manual does walk through some of those additional steps too, so it does some hand calculations in here. So this is a great, this curriculum section over here is a great utility to incorporate in some of your classes. So maybe I'll pull that PDF up. So this is the one I was just talking about. So this whole thing, you just install the student edition, and you have access to this. It's a 186-page document, but the lesson plan they go over is this one's an SAE one, so this one's gonna be all formula SAE type stuff. Introduction, using assemblies, creating weldments. Okay, kind of like what we took, using molds and surfaces, brake rotor. Here they do a thermal analysis on a brake rotor. See how much it heats up. Here's the frame analysis I just showed you, a little sample of that. If I jump down to that, it's on page 143. And then also a flow simulation on an intake. Walk you through all that. So let's fast forward down to this little section here. Here's this frame, okay, and some of the steps all in there. Okay, so let's check that out. Again, that's right over here. Okay, right over here in the SOLIDWORKS curriculum section. So let's move on to frequency. Okay, so up to this point we showed you these two study types. So the next one I'd like to show you, before we get into this time-based motion, next thing I'd like to show you is going to be this frequency analysis for vibration. One sample, this is one little sample from Simulation Professional. Simulation Professional had a lot more tools in this list here, but I've kind of parsed it down. Things like being able to calculate buckling loads, run optimization studies. But for now I've just pared down just one little quick study here for frequency analysis to show you how your students might set something like that up and what they can do with that. So this frequency analysis idea, we're going to calculate resonance. So here's an example of where resonance is bad. Of course, maybe everybody on this call is already pretty familiar with the Tacoma Narrows Bridge. Collapse due to resonance. They think that it's due to the wind. There's a wind load going across the bridge, causing some vortices on the back end of here to kind of swirl up and down at just the right frequency that it matched with the resonant frequency on the bridge, eventually leading to the collapse of this bridge. It's one common example of where doing a vibration analysis can really help. Now, in the example I'm going to show you is just something simple to get the idea down on here. A simple tuning fork. I want to calculate the resonant frequency on this tuning fork model. So here we've already drawn our tuning fork. Just want to show you what it takes to set up a study on something like this. If I create a new study, and this time instead of using the static analysis tool, I'll jump down to frequency. Run a frequency analysis. And here, in this case, I've already got my material applied. That's because in SolidWorks I applied the material. So that automatically got copied down to my simulation. And all I need to do here to set up my frequency study to calculate resonant frequencies is maybe just put a fixture on here. I'm just going to say it's fixed here for a moment. Okay. And now if I just run that study as is, could we have made that any easier? You know, if I run that study as is and animate, if I just right click on any of these plots in here and select animate, okay, now I can see it resonating. In this case, up and down. And it's resonating up and down because, well, because I fixed it over here. And this is, and if you know how tuning forks work, you know this is not a frequency that produces an actual tone that your ear can hear. Okay, if it's swinging up and down like this. Okay, as a matter of fact, I'd have to be holding it pretty firmly here for it to be swinging up and down. This is behaving as though it's like welded to a wall or something. So it's handy to be able to see how it's vibrating, to be able to question, is this a real frequency or not? And we see up here, it's according to our study, it's vibrating at 230 hertz. Now what I'm expecting from this tuning fork, based on its design, I want to see it vibrate at 440 hertz. That's so I can tune this to the note A, on the musical note A. 440 hertz is going to correspond with that. 230, it's not what I'm looking for. Now I'll have to start looking at some of these other mode shapes and see if any of these line up with the one I'm looking for. Maybe amplitude 2. If I animate that one, well, that one's kind of similar. It's just going side to side instead, also around 230 hertz. What about amplitude 3? Is this one giving me what I'm looking for? Still not. This one's this is what I call a rotational mode. If you think of it, it's like rotating back and forth around the around an axis that's sort of going through the center of this. Okay, it's like a rotational resonant frequency at 420 hertz, getting close to my 440. Finally I get to amplitude 4, and if I animate that one, now we're seeing it. Okay, this is one where it's like it's clapping its hands together. And if you think about it, that's when you clap your hands together, it's like you're pushing air together. Well, it's the same kind of principle with a tuning fork. These two tongs moving together, it's pushing air together, and we can see according to this, 440 hertz. Well, a little high. So we can make a quick change. I want this to read closer to 440 maybe, and right now it says 444, roughly. So what can I change about this to bring it more in line? Should I make it shorter or longer? How's that going to change the frequency? And this is the type of thing your students can experiment with. Okay? With SolidWorks, they can just make a quick change. If I just double click on one of these faces, 74.5. Let me test if I make it a little longer. Is that going to bring my frequency down? Okay, so make it 0.5 millimeter longer, and then just rerun my study. So instead of 444, what do we get? Now I get 439, I guess, if I round it. So that brings me closer. It actually brought me down, but it brought me down a little too far. So now I can kind of tweak that dimension a bit more and get it right in line with 440. If that's my target, start shaving off some of that material I just added on to it. And of course that maybe hopefully matches with our intuitions. If we make it longer, okay, longer makes it a little more flexible, that lowers its natural frequencies. If you make it shorter, it's more short and stubby, more stiff, that'll raise its resonant frequencies. So that's a quick vibration study using the frequency analysis available with Simulation Professional. Alright, so this shows a faster animation of those same resonant frequencies. Here I'm just showing an animation that just shows 2 frames, and I bumped the exaggeration scale down a little bit to kind of give it more of a sense of, you know, when you strike it on a table, it's kind of like what it looks like. What I'm going to take a look at next is this tool here, running time-based motion. So this is a bit of a change of gears. This tool has a different interface than the one I've been showing you with these structural analysis tools. So let's show you what we're going to do with this motion example. So here I've got a car jack lifting a vehicle. Looks kind of like an SUV. Now, the precise design of the SUV is not what I'm interested in. Okay, I just want to model the mass of it to represent it. And what I want to see here is, as maybe we want to put an electric motor on here, I want to see what the torque curve looks like as this thing rotates. Does it get easier? Does it get harder? Can we redesign this linkage a little bit, make sure the joints aren't it's not going to cause the joints to fail. So basically, I'd like to test out lots of positions, and we're going to use motion analysis in order to be able to run this. Let's go ahead and show you this guy. Okay, so here's our car jack model. Now, I'm not going to include the entire car and everything in this simulation, because I'll have to model in contact, and that's something I can talk a little bit more about. How do we model contact and everything. But I'm going to start simple, show you how to set up a quick motion study. Now, in this case, I've got this link though kind of free floating, and what I want to do is I want to mate this into place. I've already got everything else mated into place, such that take a look when I rotate this guy. So you can see it lifting slowly. Let me undo all that rotation. It's because I've already got these assembly mates on here. The SOLIDWORKS motion tool I'm about to show you, it's going to depend a lot on your SOLIDWORKS mates. How good are you at assembly modeling in SOLIDWORKS? So if your students don't know how to create assemblies in SOLIDWORKS yet, that's something they'll maybe need to get familiar with before they jump into running a motion study, because these mates are going to be important to creating your motion studies. Now, I'm going to go ahead and add a couple mates to this to put this link in place. So if I use my mate tool, I'll go ahead and just grab this face and that one. That'll line them up to be concentric automatically, since they're two cylindrical faces. Looks good. I'll do the same here to maybe there. Okay. And then I need one more mate though. This thing is able to slide in and out like this, so I'm going to add one more mate that just keeps it hooked to that face. Okay. Now you'll notice, in order to run the motion study, I didn't need to necessarily model in every little pin and bolt and fastener. Just modeled in just the key things that I want to include to be able to see how much torque is required to lift a car. Modeling in all these bolts and stuff may not be necessary. So now I'm going to move into creating our motion study. So up to this point I haven't done anything other than just some assembly stuff. So here is the SOLIDWORKS motion tool, just right bundled with all the other add-ins here. Even the example, if I hover my cursor over it, shows looks like a little valve opening, closing, motion analysis. If we go and enable that, turns on the full-blown SOLIDWORKS motion analysis kinematic tool that uses the Atoms solver. If any of you have ever heard of it. And right down here is where I go to set up a new motion study. Key step that you'll have to remember and have your students do if they set up their own motion studies, you're going to have to make sure you set this to motion analysis. And another recommendation I have for you if you create your own motion studies is disable playback of view keys. Just turn this off, because otherwise this is kind of handy. This will animate camera views and kind of spin around your model. If you don't plan on using those camera views, it's a good idea just to disable this so it doesn't keep resetting the view on you. So every new motion study you create, maybe you'll want to jot that down. Just set this to motion analysis and disable playback of view keys. And then now we're going to set up our study. Across this little bar here, we've got our motor tools and our ability to apply forces and springs, all sorts of other elements. Okay, but it's really this little subset of tools that we're primarily going to use. Motor, we're going to start with. I'm going to apply a motor onto this guy. If I just select this face, it's going to do a couple of things for me. Okay, right over here it puts that face into two boxes, but it both defines what is being driven by the motor and also the direction in which it's being driven. It's going to fill out both of those boxes. Now, since I selected this nice cylindrical face, it's going to use the axis to drive the direction of this motor. But I will flip it around. Because remember, I have to have this going kind of like a righty-tighty to tighten this, to pull this forward in order to lift. So just need to flip that over. And I'll tell this to go at, I don't know, let's try 120 RPM. About 2 revolutions per second. And at a bare minimum, that's all I need to do to be able to see some kind of results. I won't get accurate results yet until I add a force to the top. But if I were to just hit this little calculate button right now, just to test it, see what my motor's doing, Let me go ahead and play that back. Now that I've calculated my motion study, now let me go ahead and play it back at real-time speed, 2 revolutions per second speed. It looks pretty good. I'd like it to go a little higher though, so I'm gonna make this go, instead of just 5 seconds, I'm gonna tell it to run for 10 seconds, and then calculate that. And that'll be a nice sample test range we'll try out. Now, I need to put a force on the top of this, otherwise there's nothing really resisting this. I'm not really lifting anything. So let me go ahead and add a force to the top of this this guy. I'm going to put the force onto this face. Now, by me selecting that face, it doesn't know which direction to apply the force because I've selected a spherical face. So I will need to tell it a force direction. So I'll go ahead and fill out this box and I'll use this cylindrical face, because that's, the axis of that face will define that direction. So it puts a blue arrow indicating that direction, and I'll key in 2000 LBF. So if you key in LBF, it'll automatically convert to whatever the document units are set to, which right now the documents are set to metric, so it converts it to newtons for me. All right, and that's pretty much it at a minimum. Let's go ahead and recalculate it. And I won't really see any difference to the kinematic behavior of this. It's still rotating at 2 revolutions per second, so we won't really see any effect of that load until I look at some of our results. And this tool here, they should make this button a lot bigger. Okay, this is the key. When you set this to motion analysis, it makes you able to use this button to look at results in plots. Okay, so this is the very key button for looking at our motor torque. So in this case, my result that I'm interested in is going to be a force. It's more of a torque, and under here we have motor torque. And you can see it's not so intuitive. There's just a lot of options, a lot of different kinds of results you can look at. Okay, and you just gotta browse through the list, see what's available to you. Okay, but in this case, motor torque. And then finally, I want to look at magnitude. And now here it's like, what should I select in order to get this to work? You might try to pick in your screen, try to pick on faces. Again, not so intuitive until you hover your cursor over this box. That's the key here. This is one step you might want to remember or jot down if you want to run your own motion studies. If you hover your cursor over this box, it gives you a hint. It says here, based on what you've picked here, since you're looking for a motor torque, if I hover my cursor, it says select a rotational motor object. So that little hint is really important to know what it's looking for for you to be able to make your pick. So select a rotational motor object. Well, the only place where I could see where I could select a motor is down here. I'll click on it. And there we go. Now it grabs that motor. And now if I click OK, let's see what that torque looks like. And there it is. And did you expect that for it to be the torque decreasing? Torque starts high and it starts decreasing as we go along. It gets easier. Does that make sense? So let's kind of roll back here a little bit. Let's just do a quick gut check here, see if that makes sense. And so you can see as I drag left and right, it kind of updates that position and everything. So I can see here large torque, and then it gets easier. It gets easier. Okay, large torque here, less torque there. I think that makes sense because you see, really, when you look at it, think of it as like we're pulling on this. When we're rotating this, we're pulling on this, pulling on it in this direction. And you can see the distance between this axis and this guy is pretty small. It's like we don't have much leverage. And then as we move along, we get more and more leverage. Picture now we're pulling on that, but now we have a bigger lever arm. Okay, so that's the kind of behavior we're getting. Now we can use that insight maybe to make a better design or maybe tweak the design. Okay. Now you can even do things like including friction in some of your joints. Right now, assuming everything's frictionless, we get a result of 7211 Newton millimeters. Now I'm just going to maybe jot that result down for a moment. 7200. Let's see how that compares if I just add a little bit of friction. Okay, so this is where it gets a little bit tricky if you want to do a hand calculation for this kind of thing. Maybe we can get away with it here, but as soon as you start adding friction to joints, it becomes a little trickier, and a numerical solver comes in more handy. So I'm in my mates folder here. I've got this hinge mate. There's this hinge mate over here, and that's holding these two things together. And if I edit that hinge mate, I've got this analysis tab. Okay, this is available when you turn on that SOLIDWORKS motion add-in. It adds this motion analysis tab where you can do things like add friction to your joints. I turn on that friction, and I'll use a pretty low coefficient here, maybe 0.1, or maybe no. Let's do steel greasy, 0.05. So let's see how big of a difference that makes. If I go and recalculate, am I going to see any difference to the animation here? I shouldn't. It's going to still rotate it at the same exact rate that I told it to, 120 RPM. But where I'll see the difference is in my force result. Anybody remember what result I had before? 7,200, right? Now just a little bit of friction, big difference. 30,000. Factor of about almost 4 times higher for torque required. So that means we need a motor that's 4 times bigger to try to lift this thing. So that's a simple SOLIDWORKS motion example. By the way, this is also another model that is included in the SOLIDWORKS curriculum. If you'd like to use a model like this, this one is in the let's see here. I think it's in the 2016 actually. It's part of this Fundamentals of 3D Design and Simulation book. Now this book, if you download the English version, basically what they've done here is they've taken our commercial training classes and they're giving away some of that content for free. It's sort of like a sample of the commercial training classes. What they do is they took the first half of our SOLIDWORKS CAD class, roughly, put it into here, and they took lesson 1 out of our SOLIDWORKS motion class, lesson 1 out of our SOLIDWORKS flow simulation class, and lesson 1 out of our SOLIDWORKS structural analysis class, and they put them into this manual for you. Okay, so you can get a quick that rectangular block that had the hole in it. There's a PDF that'll walk through some steps in there that you can show to students to get them started with some of these tools. This example and the block with a hole in it so far are ones that I've pulled right from here. And I'll show you a few other little slides here that show other things you can do with SOLIDWORKS motion. So here's a few more motion examples if you want to get more sophisticated with it. Here I've got sort of like a planet. Think of it Earth, and then we got the moon going around it. And this is just using Newtonian physics. Okay, I've put in a force couple that the force depends upon the distance between these two objects. Okay, you can apply force relationships that depend on some results, so that and this is again all using the Adams solver in the background, so you can do some pretty advanced stuff with SOLIDWORKS motion. Here's another example. It's just more of a, which path is the quickest to roll down. We just turned on 3D contact, turned on gravity. So gravity, you turn on this apple here, and you tell it which direction that's going to be pointed. Okay, point it downward. So we turned that on, and then we also turned on 3D contact. We selected this contact option and told it that the ball is not allowed to penetrate through the plank or something like that. We told it these two things are contacting each other, and it's maybe a stiff contact with some friction. And then for that force example, if you want to apply a force that depends upon a result, you can do these expressions where I can say this force is equal to if you wanted to create a torque curve, you could do that. You could say my force is equal to torque times 2 or something. You can enter in your own expressions into here. If you want to key in a motor curve, you'd have a torque that depends on the angular velocity of the motor, and you end up getting a realistic looking motor result rather than one like this which just powers through it, 120 RPM. Then also this example here is just kind of taking that linkage to an extreme here. We have one motor, this little red gear here is driving all these other gears and causing this little pig to walk across the table or across the floor. See how much torque's required on that motor to actually have this thing move, and how big of a motor do we need to drive it. So this is actually from a University of California, Irvine, UCI, where one of the instructors there, he teaches a class that due to COVID, he actually has people build this stuff normally, but due to COVID, he decided to make his class completely online and just use SOLIDWORKS motion for the actual construction of this. He used SOLIDWORKS motion so that they don't have to meet in person to build it all. It's a really cool example of SOLIDWORKS motion in use at a university. Other examples, more examples that, a lot of people relate to sports, so it's easy to get students interested sometimes. If you show them like some contact examples here. Here's one where I just turn on 3D contact between the bowling ball and in the lane. And also friction. There's two different friction regions. Okay, in the center of the lane they have it well oiled, so the thing slips pretty well, but near the end of the lane it's not as well oiled, so it catches. So you can kind of tell that effect happens near the end. It catches and then we hit a strike. Okay. Here's an example with a tennis ball that's going to curve. You're going to see this tennis ball curve in midair, and the curve is going to be based on its rotation. Depending on how it rotates, it'll curve. And that's because I put a force on this tennis ball, a force that's depending upon the direction of rotation and the rate of rotation. So I included drag force and lift forces. So you'll see this ball's hit. It's got some spin on it. It curves around and lands in the singles court. So you can kind of tell that curve there. And this here was using a trace path inside of SOLIDWORKS motion. You can look up trace paths if you want to show that kind of stuff. You can show projectile motion using SOLIDWORKS motion if you want. Another contact example is just a billiard ball. Now what's special about this one? It's a lot of contact, but really it uses the photorealistic rendering tool, PhotoView 360. You just turn on a little switch when you go to save the animation that you created. You turn on a little switch to tell it to use the photorealistic renderer, and it creates a much more realistic looking image. This came right out of SOLIDWORKS. Much more realistic looking image. You see kind of the shine on the balls and everything. Now it does take a lot longer for it to save that because it has to render every single frame of that animation. So this took hours to render. And finally, this last one, just more 3D contact. Going down a slide, and also it just shows using cameras. I can hook a camera onto this. Think of it as like a person in a tube or something. You hook a camera on that, and then watch them go down the slide there. It's part of that little thing I disabled, that orientation and camera views. You leave it on, and you can hook a camera onto stuff. You see it kind of comically falls off on the end there. So we might want to consider a redesign of this slide. Maybe add a little more support on the side there. All right, so that is the the time-based motion included with your EDU and student editions. So let me show you some of the quick flow study as well. Show you how easy it is to set up one of these, and I'll do a simple one where we'll calculate drag on this block. Okay, and then we can compare. I won't go through the whole comparison. I'll just show you the setup on a simple drag study. A lot of students might like to be able to maybe draw the body if it's a Formula SAE, or if it's an airfoil, like to be able to draw that body and then run a flow study on it, figure out drag, then make some changes to it, test drag again. So here I've got a simple model, and if I want to run a flow simulation study, I'll turn on SOLIDWORKS Flow Simulation, just like the other add-ins that we've already played around with a little bit. Now, and just like the SOLIDWORKS simulation tool, when I turn on that add-in, it adds a flow simulation toolbar to my command manager, and I can set up a study using either new or wizard. Now what I like to do is I almost always use the wizard option, unless you've created your own templates. Then you can use those templates to create quick and dirty flow studies that uses those templates. Now I set up a lot of different types of studies though, so I like to start with the wizard. So with this wizard, it's going to walk me through the steps of setting up some of the background details behind the flow simulation. Things like, do I want to include radiation, thermal radiation? Do I want to include heat conduction, gravity? Are those going to be important? Physics? What kind of physics do I want to account for? It's primarily one of the things this wizard is going to ask me along the way. So I'll go ahead and I'll use the default project name, nothing special there. Units, I'll use the default unit systems, but you can create your own custom sets of units. So I'm just going to next through a lot of these steps. Now here I do want to make sure I run this as an external study. That's going to be like flow around a cylinder or around a body, versus this would be more like an internal flow. This would be like flow through a pipe, okay, or through an intake manifold for those Formula SAE guys. So we're going to run this external. I'm not going to include any heat conduction or gravity or anything like that. I'm going to put this in air. Okay, so I'm going to go ahead and grab air for my fluids instead of water or something. If you're modeling a submarine or something, you might use water here instead. And for the rest of these, I'm going to use default wall conditions and default initial conditions. These won't so much matter in my study. The wall roughness may matter, and that might be something I want to come back and tweak, but we're just going to assume smooth wall to start with. So once I hit finish, now it wants to know how fast do I want the fluid moving. So that was actually something I just skipped past. In order to get back to that wizard, I just got to go to my input data here. This is where all those settings I just created was under input. If I go back into there, I can go back to that step I forgot, which was the key in the velocity that this thing's moving. I'm going to say it's moving at a decent click, about 10 meters a second in the X direction. Alright, so now that defines my flow velocity going around this thing. And actually, that's pretty much it for setting up a study like this. If you're just trying to do drag calculations, I could just hit run. Now, it's a good idea to play with the mesh and also set up some goals. It's not a required step per se, but you'll get more accuracy if you do tweak the mesh a bit, make it a little finer in regions that you're interested in. And also, it'll be faster to run if you set up a goal and let Flow Simulation know what it is you're trying to calculate. So I'm going to set up a quick goal here. It's going to be a surface goal onto all these faces of this body. Okay, I'm going to monitor the force acting on all those faces. So I'll do force X. That's going to monitor the force. That's my drag force. Equivalently, I could have just set up a global goal and set it. That way it would have grabbed all the faces. I didn't have to do this surface goal business. Okay, but just want to give you a sense. It's grabbing all these faces and looking at the X direction force acting on all of them. Also my mesh. Just want to show you one quick mesh here. If I show the basic mesh, you can see coarse mesh, fine mesh. We keep it simple. Nice simple slider here that I can move back and forth. I'm going to leave it set to this default level 3 mesh. And I'll go ahead and run this study. So go up here, click on run. Just this. Very similar to the structural analysis tool as far as the way it's all laid out. Okay, and it actually was made by a different developer altogether, but they kind of copied the same way we did the structural study a little bit. Okay, so it's nice that your students, they won't have to learn 2, 3, 4 totally different interfaces. You know, there's some consistency between the different studies. Here, as it's calculating, because I created that goal, you know, since I didn't create a temperature goal, right? I didn't ask for what's the maximum temperature or anything like that. I asked for drag force. That's why it's showing me the force in the X direction here. And it looks like it's stabilizing somewhere around 0.6 newtons or so. If I customize this a little bit, just so I can see what happens here. I can kind of zoom in on the scale. I can see it oscillates a little bit. Probably getting some of those vortices like on that bridge. That Tacoma Narrows Bridge, it's probably going to oscillate back and forth. But it looks like my drag force is going to be somewhere in that ballpark of about 0.65 newtons, plus or minus 0.05 newtons or something. So I'm going to go ahead and interrupt this study. I'll go ahead and say it's going to complete right around 98 iterations, 98 steps it took. And it says it's done because it sees that it's just fluctuating up and down, not changing a whole lot. And now we can take a look at some of the results. I'll animate some flow trajectories for you. So under my results folder here, I can use this flow trajectory tool to animate. If I use this is actually a pretty new tool, this little rectangle tool here. So if you have like an older version, then you might have to do this a little different than what I'm showing here. Okay, I'm going to put a rectangle a little bit upstream. Kind of line it up like right in that region right there. You'll see what this is doing in a moment. You see these little blue dots that are on here. Those are important. Let me bump it up to 100. You see a lot of little blue dots. And then I'll animate arrows. Okay, kind of shows me what that solver did, when I ran the study, what happened there. And another thing I'm going to do, let me move that thing back. Let me move this over here, actually. Let me move it back here. See what's happening on the back side of it. Might see more circulation. Hey, check that out. Play that. Putting those dots back here, it's probing. It's creating little probe points for it to create these streamlines. Really, they're streamlines with a bunch of arrows on top of them. I'm not sure how well that plays through in the over zoom, if it's smooth or if it's a little choppy. If I zoom out a little bit, usually it's a little smoother. It looks really smooth on my display, but that's because I'm not, you guys are transferring this stuff over the internet. Ultimately, though, the key item that I was looking at here was that drag force, but you can kind of see why my drag force is the way it was, because of all this turbulent loss of energy back here. We're getting a lot of drag. If I look at some surface plots of the pressure, we can see on the front there's higher pressure, on the back there's a lot lower pressure, because of we're losing a lot of that energy due to a lot of turbulence that these edges are creating. Now, based on that drag force, we can calculate drag coefficient. You divide by the area and use the dynamic pressure of the fluid incoming stream. You can calculate drag coefficient. Other things you can do with flow simulation. This shows the same kind of thing done at a much larger scale. Here I've got that old Tesla Cybertruck compared to a Chevy Silverado, compared to a bus or like a streamline shape, showing different turbulence generating from that to calculate drag forces. Here's a airfoil where I'm actually tipping it a little bit as we go. We're changing the direction of the incoming airstream, and we're seeing at what point does it stall. Right there, it starts to stall at that angle. Here's like a flow meter, okay, where we set up a study such that it runs at a bunch of different positions. We set one up that runs here, runs here, runs here. We ran like 50 different studies to produce this animation. We can do rotating geometry and moving walls. These are like for mixing applications, or for if you want to simulate, if your students need to simulate an impeller for any reason, calculate a fan curve. Might be an interesting exercise for them. And also heat flow. Flow simulation is very good at heat modeling. Here we have HVAC on the left here, where it's here's a building where we have a furnace running. You can kind of see the hot air coming out of the furnace, and we see that these two rooms get a little cooler than some of the other rooms. Thermal radiation example, showing reflecting off of this and focusing it. And then heat sink, okay, where we can look at heat transfer directions. And finally, last couple little vignettes here. If anybody doing the concrete canoe project or any kind of canoe design, okay, we can run a free surface study on that. And here's a hot water heater, just to show you filling a tank. Okay, showing the volume flow rate of the water as it's coming in. So quite a few other applications for SOLIDWORKS flow simulation. But again, probably the most popular use I see for it is either for like an intake manifold simulation to try to balance the intake, or to calculate drag and then make changes and recalculate drag, or lift if you have like an airfoil on the back of a spoiler of your formula car. All right, so with that, wrapping up. So included with your EDU packaging is all of these tools. Okay, so we covered the linear static, the time-based motion, a little bit of frequency. But a lot of things that we didn't touch that are also included. You know, if you have students that want to do an impact attenuator impact test, you know, this drop test tool is good for that. Or if they have I'm being a formula essay, I'm just hammering on this formula SAE idea because that's the one specific example I know for university. But buckling analysis for things like the tie rods, not the tie rod per se, but the other rod, the one that's in compression. You can do a buckling study on that. And then edge weld connectors, a lot of other tools that are available as well, all included with the EDU package. And then, just like I said on the flow side, includes an electronics cooling module, an HVAC module, and even some injection molding plastics tools if you're teaching students about injection molding plastics. So other resources where you can go to direct some of your students. That help pull down in SOLIDWORKS should be the first place. If you go to the SOLIDWORKS help pull down, that student curriculum thing that I've been showing you, that's right in there. It'll bring you right into that little folder I showed in the interface. But there's also a website for student resources and instructor curriculum. You create a login, you can check some of that stuff out. Some of the student curriculum requires downloading the SOLIDWORKS training files from a separate source. Okay, the one that I mentioned about having it where we pulled lessons from our actual commercial classes and put them into that document, you may need to download the actual full-blown SOLIDWORKS training file set. These are publicly available, but we don't have the commercial training manuals online publicly available. Okay, those have to be purchased. But at least the files that you could use for some of those sample documents, they're all right here. If you just do a search for SOLIDWORKS training files, you'll find these simulation, SimPro, flow simulation files that you can use as examples to help teach students. Also, secondary resource, tutorials. Tutorials are nice. They're built in to the SOLIDWORKS interface. You'll also find these in the help pull down, but you have to turn on the add-in first. Once you turn on the SOLIDWORKS simulation add-in or the flow simulation add-in, you'll find it right here in this little tutorial section. Or actually, there'll be a simulation section that has tutorials. Okay, but once you turn on those add-ins, you'll be able to get access to these tutorial documents. This is a flow simulation tutorial. It's 322 pages, so plenty of little applications in there. Also, our YouTube channel. Okay, we have dang near 2,000 videos on our channel, or if you just search YouTube for content, SOLIDWORKS is probably the best CAD tool for this type of thing. There's so much content on YouTube. It's hard not to find what you're looking for, especially if you go to YouTube, type in Formula SAE. And finally, one last resource here. If you go to gou.teachable.com, we do offer training classes on here, but these are more on a paid basis. So that concludes our presentation today. Thanks everybody for attending.